Okay, so in this video, we're going to be creating a calculator in Excel to calculate the 2x2 determinant and an inverse. So we're going to start by putting in our A matrix. And let's say I want to calculate the inverse of 2, 4, and 1, -3. So this is my A matrix. And so over here, I'm going to calculate my determinant of A, which is going to be, again, relatively simple, but we'll use this to build determinant calculators for bigger matrices. So the determinant of A is going to be this entry times this entry minus this entry times this entry. And so then our A inverse. Now recall the formula for the A inverse is going to be, we're going to switch the positions of A and D. So that means this entry right here is going to be this one. And this entry right here is going to be this one. And then the opposite to B and C positions, they're going to stay the same place, but they are going to change sign. And then the whole thing gets multiplied by the reciprocal of the determinant. So each one of these positions then will become the value divided by our determinant. Now, if we want to express this in fraction form, we actually can. So what I'm going to do is I'm going to recreate this, again, by just copying these entries for the time being, so that I can format them differently without affecting the original calculator. Now, these entries, what I want to do is I want to reformat them as some different number formats. So maybe I want fractions. Here's a fraction. Now, the thing about the fractions is the default is to convert everything to fractions that have only one digit in the denominator. And that's not what I want. So if you choose this, sometimes it'll be correct. The 1/5 are going to be fine. But notice that the 1/10, it converted to 0 because it's not big enough to round to a fifth. So we're going to go to the more number formats, and under fraction, you can choose up to 3 digits in the denominator. And then what Excel will do is it will reduce it, it'll simplify it to as simple a fraction as it can, but it will include up to this many digits. Now, in a class, in a textbook problem, you're unlikely to have determinants that have this many digits. So it's probably safe in most cases to use 2 digits, but I always default to the 3 digits because it gives me the most accurate answers. And in those rare circumstances where you do get like 110, you don't have to worry about the weird rounding. And so now everything looks good. We've got our 3/10, which is what we would expect here, 2/5, which is 4/10, 1/5, that's 2/10, and then here's our -1/10. And so this would be our inverse in fraction form. This would be our inverse in decimal form. And if you wanted to, you could even just have the entries without the 1/, multiplying them, just to kind of, when you're doing calculations, sometimes it's easier not to work with all of the decimals and save multiplying the fraction through at the end. And so if you just set that up without the reciprocal, and then just indicate over here times 1 over the determinant as your reminder, then you have sort of the whole number version, you'll have the fraction version, you have the decimal version, you have a bunch of different versions. And again, the nice thing about this is that once it's all set up, you can just go ahead and say, okay, well, I need a different matrix. Let's try 4, -3, 5, 7. Boom, everything gets updated. Our determinant now is not 10 anymore, or -10, it's 43. Our fractions are expressed in 43s. We have our decimal version, which you don't really want to work with per se, but you also have your whole number versions over here. Just remember that you need to multiply the whole thing times your reciprocal of your determinant. So you've got different versions of your inverse here. And again, this is useful for just checking arithmetic, making sure that you don't lose a minus sign or things like that as you're going through and doing your calculations. And this way, you have all of it set up, and you can save this so that you can go back and use it as a check. Especially, for instance, I mean, you can do all of this in your TI calculator, for instance, but who wants to spend $100 on a calculator if you don't need to?